Good morning, class, and today we're going to talk about normal force. So, what is the normal force? Well, when an object is on a surface, the normal force provided by that surface is the force that keeps the object from breaking through the surface. So, let's get that written down here. It is the force that keeps the object from breaking through the surface. So if we think about this, if there was a floor and you put an object on the floor, the normal force is the fact that the floor pushes something up to keep that object from breaking through the floor. That's a normal force. It's always provided by an object on a surface and is to keep it from breaking through that surface. So how big is the normal force? This is something that often gets a whole bunch of students and a whole bunch of mistakes. So let's make sure that we get this 100%. The normal force is always exactly as large as it needs to be to keep an object from breaking through the surface. So we can calculate the size of the net force using, or the normal force, we can calculate the size of the normal force using our net force equations. Using a little bit of net force will help us determine things because the normal force keeps things from breaking through. The normal force is not the same size as gravity. Please don't make that assumption. Let's look at a few examples. So a 5 kilogram box is sitting at rest on the ground. How large is the normal force on this box? Well, if we're going to solve this through net force, we have to start with a free body diagram. Here's this box on the ground. And what forces are there? Well, ground means earth, earth means gravity. But ground means it's a surface, and a surface provides a normal force to keep it from breaking through. Now, there are no other forces set in this problem, so we don't add any other ones. So when we look at our net force equation, we ask, okay, well, what does my net force equation look like? Well, these are the only two arrows, Fg and F normal. So that's pretty easy. I just get to say, well, it's gravity minus my normal force. Or you could alternately do normal force minus your gravity. It's the same thing. So how can I use this to find my normal force? Well, ask yourself a question. Is this box moving? And if you think about it, well, the box is sitting at rest on the ground. Is the box going to go anywhere? No. So we see here that the acceleration of this whole situation is 0 meters per second squared. So we get to use that in our net force equation. Since this is mass times acceleration, or 5 times 0, well, that'll be easy. Now, you might be like, well, we don't know any of the others, but hey, we already always know how to find the force of gravity. It's going to be the mass times 9.8, at least while you're on Earth, right? So this will be the mass of 5 times 9.8. And 5 times 9.8, if I remember right, is 49 newtons. So, yeah, 49 minus normal force here. So then we have 0 equals 49 minus the normal force. And if 0 equals 49 minus the normal force has to be 49, because only 49 minus 49 would equal 0. In this case, in this specific situation, was the normal force as large as gravity? Yes. In this specific situation, it was. Let's look at a couple more so we don't get into the habit of saying the normal force is the same size as gravity, because it isn't. All right. A book is being pushed into a wall by a 400 Newton force. How large is the normal force on this book? Okay, well, to draw this, I have a book and a wall. Now, what things do I know about this? I know that there is a force that's pushing the book into the wall. I don't know what's causing this force, so I'm just going to call it an applied force. There's a force applied to the book. 400 newtons, pushing it into the wall. This is assumedly on Earth, so there's probably some gravity. And the normal force is the force provided by the surface to keep it from breaking through the surface. Well, what force is trying to break through that wall is the applied force. So the wall needs to resist it to keep it from breaking through. It's going to apply 90 degrees outward because that's perpendicular. That's the normal force. So there we go. We got normal force pushing out that way. Now, how would I figure this out? Well, net force here. Where is this object accelerating? It's probably going to be slipping down unless there's some friction. But if I look at my normal force and my applied force, is it going to be going left or right? Is it going to accelerate left or right? And the answer is no. The acceleration is actually 0 left or right. It's not going into the wall. It's not going out of the wall. So I could make this my left and right net force equation. And my left and right net forces are the applied force and the normal force. And again, since the acceleration is 0, that means my total net force is 0. So that shows here that 0 would be our applied force, or 400 newtons, minus our normal force. Well, if we don't know how big it is, that's okay, because 0 equals 400 minus force friction. 0 is 400 minus what? 400 minus, well, it's got to be 400. The normal force here is 400 newtons. Whoops. Now, if we take a look, ask yourself, how big is the gravity in this situation? Well, the gravity is the same as it was in the previous situation because it's a 5-kilogram book, so it's 49 newtons. Was our normal force the same size as gravity? No, it wasn't. In fact, it had absolutely nothing to do with gravity. For our next examples, take the time to pause the video and try to solve it on your own. This problem, you might recognize, this problem is actually one of the problems that we had from our free body diagram literacy assignment that we did just last week. Let's go ahead and let's do this, but now we are going to solve for the normal force on this iron. A 33-kilogram piece of iron is placed on the ground, and a strong magnet is placed above the iron and pulls upward with 200 newtons. Force magnet. 200 newtons pulling upward. Determine the normal force on this iron. Well, thinking about this, we got some gravity. And now gravity is going to be our mass times 9.8. Right? So if I were to bring up my calculator, 33 times 9.8, 323.4 newtons. So gravity is pulling with 323.4 newtons. If I was to look at this situation, and this situation alone, gravity is bigger than the magnet force, isn't it? That means it wins, it pulls harder, and that means the object will accelerate downward. But what's the problem? Is the iron's on the ground. Will that iron dig into the ground? No, it won't. It's because we are missing a force. We're missing the fact that the ground can provide a normal force to keep it from breaking through the ground. So it provides a normal force to keep it from breaking through the ground. We don't want it to break through the ground. That's the whole point. The ground doesn't want that. So how big is that normal force? We have to use a net force equation in this case. F net. Now, looking at this, I'm going to go ahead and make my winning forces. Maybe I'll choose gravity as my winning force. And all the forces working against it, like the magnet force and the normal force, will subtract from it. Now, this is all good. We just have to ask ourselves, hey, where is this box going? Is this accelerating? No, it's not accelerating. The magnet isn't strong enough to pull it off of the ground because gravity is stronger than the magnet. And gravity won't be strong enough to break through the ground because the ground's pretty tough. So the ground will be able to provide a normal force. So our acceleration is again 0 meters per second squared, meaning our net force is 0. So we can solve that here. Have 323.4 minus our magnetic force, 200, minus our unknown normal force. So I'm going to bring these two numbers together. 323.4 minus 200 would be 123.4. And how do I make those 0? Well, if 123.4 minus a number equals 0, then that number has to be 123.4. The normal force is 123.4 newtons. That's exactly as large as it should be, and some of you already actually figured that out last week. So good job on you. If you had struggles with it, this is how you find the normal force. Can you notice here, is the normal force as large as the gravity? No, it isn't. It's not as large as the gravity. You can tell that I want people to stop making this mistake. Okay, I think we've got 2 more problems. Let's go ahead and let's speed through these. Joe is standing in an elevator that is accelerating upward at 2.2 meters per second squared. Determine the normal force of the floor that the elevator is providing on Joe. So here's Joe. I'm not even going to bother drawing the elevator because I don't care about the elevator. I'm interested in looking at what Joe is doing. So I'm going to have my free body diagram of Joe. One thing that I know is Joe has some gravity, and the floor is pushing upward on Joe, keeping him from breaking through the floor. Now the normal force, again, we can find taking his mass, multiplying by 9.8. So 60 times 9.8, let's go ahead and do that. 60 times 9.8. So 588 newtons. That's how big the force of gravity on Joe is, 588 newtons. How large is this normal force? We don't know. So, well, it's just a matter of making a net force equation. Now, if I consider who's winning, well, look at this. The problem says it's accelerating upward at 2.2. That means upward is winning. So you know what? I'm going to put normal force as winning this time. I'll put gravity as losing. Now that bit I highlighted, it's accelerating upward at 2.2 meters per second. That's actually pretty key because that means our net force is not 0 this time, because net force is mass times acceleration. That means it's got to be 60 times that acceleration of 2.2. That equals our unknown normal force minus the force of gravity, which we know is 588 because we calculated it earlier. So I'm going to calculate what 60 times 2.2 is. We see it's 132. 132 is equal to the normal force minus 588. And if you're wondering, how do I solve this, or what algebra we do, we see that it's being subtracted by 588. So to cancel that, we add 588 to both sides. And we should see here our normal force is going to equal 0 to 720 newtons. The normal force is in fact larger than the gravity when an elevator is accelerating upward. Let's look at our last problem. So Wolverine, the fictional character from the X-Men comics, is stuck to the ceiling because Magneto is using his magnetic powers to push Wolvie's metal-plated bones upward with a force of 10,000 newtons. Wolverine has a mass of 136 kilograms. Determine the normal force of the ceiling that is pushing on Wolverine. So Wolverine is stuck on a ceiling. So if I was to draw Wolverine, here he is. Right? And this would be the ceiling he's stuck on. Now what's happening? Well, a huge magnetic force, 10,000 newtons, is pushing him upward. Does gravity still exist on Wolverine? Well, of course it does. There's our force of gravity. Now, how big is our force of gravity? Well, it's his mass times 9.8. So let's calculate that. 1,332.8. Taking a look at this, what's winning? Clearly, the magnetic force is winning. The gravity just isn't nearly enough. That's why Wolverine was thrown upward off of the ground and is now stuck on the ceiling. But here's the thing. He's stuck on the ceiling. Is he breaking through the ceiling right now? Not according to this problem. That means something is keeping the ceiling from breaking. That means there's a normal force provided by the ceiling keeping him from breaking through. Right? The ceiling pushes outward. This is going to keep things. This is what allows us to make a net force equation to determine what the normal force is. Let's take a look here. Is Wolverine accelerating right now? Oh, no. He's stuck. That means the acceleration of this situation is equal to 0. That means we have a balanced set of forces. So that means our magnetic force will be the same size as all the forces working against it. The normal force and the gravity force. Because our net force is going to be 0. So this is a matter of 10,000 newtons minus whatever our normal force is, minus 1,332.8 newtons. And let's just go ahead and calculate that. 8667.2. The normal force, you can see, is 8,667.2 newtons. Which direction is it pointing? We see that it's pointing downwards. So this situation is what happens when you push something onto the ceiling. Your upward pushing force is going to be countered by gravity and normal force. Notice in this situation, normal force and gravity are working in the same direction. Totally breaking the idea that the normal force should be equal in size to gravity. It is not. That's it for normal force. Have a good day.